So, welcome back, and I do hope you're well. We've been doing a bit of work on the photoelectric effect, and if you can't remember the photoelectric effect in detail, have a look at my video that I've done on FJ's Physics that explains and demonstrates the photoelectric effect. But what we're going to do today is take the whole thing a full circle and look at the de Broglie equation. Okay, so we're in the stage of physics now where people go off and do the photoelectric effect. And if you remember, the photoelectric effect is a low work function metal with a photon of light hitting it and a single photon of light ejected a single photoelectron. So that suggested that light's a particle, that when it hits a metal surface, if there's enough energy in the photon to overcome the work function, out comes a photoelectron. Okay, we've done all of that. So that suggests that light is a particle. And then you do experiments where you shine light at multiple slits. So I won't do this in detail, but you shine a laser beam at multiple slits, and in goes the laser beam. And you get places on the screen where you see light, you don't see light, you see light, you don't see it. You get these fringes, and they can only be explained by light coming through and arriving in the bright areas in phase and the dark areas out of phase. So we've got light as a particle with a photoelectric effect, and as a wave with young slits or multiple slits, diffraction gratings. But Louis de Broglie kind of thought about this a little bit more, and he said, okay, we can see a wave behaving, this is a wave behaving like a particle. I wonder if particles can behave like waves. Now if you think about it, you can imagine solid particles like an electron. How could that ever be a wave? I mean, it's a particle. You imagine it as a ball rotating around an atom in an orbit. But the physics was beginning to develop a little bit further than that, and people started firing high energy electrons at lattices of atoms. So what you need to do now is go away, pause my video, and go and look at the link on electrons being fired at a sheet of graphite in a vacuum using an electron gun. And what we see there is electron diffraction. And if you see diffraction effects, it must mean that the electron's behaving like a wave. Come back in a few minutes when you've seen that. Okay, so what did de Broglie do? Well, to simplify things, he wrote an equation, and his equation was this: lambda equals h upon rho. Okay, now it's one of the most amazing statements in physics, this. People are always asked what's their favourite formula. I think this is one of the most startling of all. Partly because of its simplicity, there's no really complex stuff going on in here, and partly because it takes two bits of physics and it equates them in a way that just doesn't seem to make sense at all. Let's be clear on what rho is. So rho is momentum, mass times velocity. And so what it's saying on this side of the equation is things have a wavelength, and on this side of the equation it's saying that those same things have a momentum. Well, okay, you can imagine a wave travelling through space, but what does momentum mean? Momentum means it's a mass moving with a velocity. So if I rewrite this as lambda equals h upon mv, just have a look at how startling that is. And I mean, de Broglie, absolute genius to think this out. He's worth looking up because he had a really interesting background and I think royal blood and all sorts of things. Perhaps that gave him time to think about stuff. Who knows? Any which way. There we go. So, things have an associated wavelength if they have momentum. Now, I know you're going to say that's utter rubbish because I've never seen my car go past the window as a wave. It's a solid thing that goes past and has momentum, so this is rubbish. Well, not quite what you'd think, because you'll notice that the wavelength of any particle, is, I'll put proportional in there, is proportional to 1 over its momentum. And the constant of proportionality is our good old Planck constant again. Now, if you looked at the electron diffraction experiment I did, we got electrons hitting basically slits, so hitting the gaps between atoms, and they produced a diffraction pattern. I mean, this kind of sort of thing, which means that the electrons which had momentum were showing wave-like properties. So you've always thought about an electron as being a particle, but now we can see a particle behaving like a wave. So an absolutely remarkable equation. So what I need to do now is to look in detail at that experiment of electron diffraction and see how we can do some calculations on that. And also I need to explain to you that as I walk around my laboratory, I'm a particle. If I'm moving around, I've got momentum. So why don't you see me as a wiggly wave running over the place? And why don't I kind of interfere with myself, as it were? That's going to take some explaining. So I usually leave this bit until last, but let's do it first because it helps us with the equation and dealing with that. Let's investigate why when I walk around the lab, you don't see wave effects with me. Okay, I usually set a question that involves playing pool or snooker, and why don't the balls hit each other and pass through each other? Or even more weirdly, why don't they interfere? Why do they just behave like solid objects? Because, am I saying this equation's wrong? Well, I'm not. So let's have a look at a human. Now, this is good physics, guys, so having the ability to estimate a little bit. Okay, so we're going to use what's the wavelength of a human. Okay, well, it's going to be equal to h upon rho, so mv, and we need to put a few little estimates into this. So what we'll do is we'll say the wavelength of a human is equal to h upon mass of a human, should we say 60 kilograms? Okay, I'm a little bit less than that, but that'll do. And we've got to get the human moving, so let's have them moving at, let's say, well, a walk 2 meters per second. Okay, so there's the momentum of our human. So we need to put Planck's constant in here, 6.6 times 10 to the minus 34 joule seconds. So we're operating in the dark here, 6.6 times 10 to the minus 34. Divided by 60, divided by 2, and we get the wavelength of a human to be in the region of 5.5, 6 times 10 to the minus 36 meters. Okay, so I hope you did that calculation. It's an easy estimate to do, but look at that number, okay? This number is, well, think about the width of an atom. So you should know that the width of an atom is about 1 times 10 to the minus 10 meters. You should know that the width of a nucleus is about 1 times 10 to the minus 14, minus 15 meters. And this is many, 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 shall we say 16 orders of magnitude smaller than the width of a nucleus. So my challenge to you is, make yourself diffract. Well, if you want to show your wave nature, you're going to have to throw yourself at gaps or slits of that sort of separation. Why do we never see any of the wave effects? Well, that's why. We can't produce any slits that are that narrow. So you're not going to see human beings diffracting at all. Okay, so now let's look at electrons. Well, you've seen them diffract. So they have a wavelength that is demonstrable in the lab. So what we did with the electrons is we had them in a particle accelerator or a cathode ray tube, and I'll just very quickly draw a small cathode ray tube like that. Okay, and all I really want to indicate here is we had a positive part in the tube, okay, that we accelerated them to from, that's the anode, from here that we made negative, and we put a voltage across these 2 points of about 5,000 volts. Okay, doesn't matter what the minus is and what the plus is, it just matters that there's a potential difference of 5,000 volts. So let's make that 5,000 volts, 5 kV. Okay, and we had our graphite sample here, so consider that to be the slits that the electrons were going through, and we saw on the screen our diffraction pattern, and it's sort of in rings. Okay. Now, I'm not going to do any measurements on this at this stage, but all I want to say is let's look at some of the maths of this to see how it works. So, we need to work out what the momentum is of the electrons, and then we can work out their wavelength. So, the electron momentum, will be equal to mv. And I'm going to deal here with rest masses. We're not going to correct for relativity. Okay. Well, we can look up m of an electron, and it's v we need to work out in this system. So let's quickly look at that. Well, when the electron moves through a potential difference of 5,000 volts, it's going to gain, there we go again, guys, EV, that many joules of energy. So that's the charge moving through a potential difference. And it's all going to be created into a half mv squared. Okay, so what we want to do is get the velocity out of this. Now, there are clever ways you can solve for the momentum, but just have a look at this. 2ev is equal to mv squared. Yep. Okay, so 2ev over m will be v squared. Yep. And then I'll put it over here. 2ev over m square root will be the velocity that the electrons move at. Well, if we know their velocity now and we know their mass, we can put that into the de Broglie equation and work out what their wavelength is, and then see if we know anything that we can sit next to each other to make a grill that will have that sort of spacing and will show diffraction effects. Okay guys, so reach for your calculators and put some numbers into this equation, and I'd like to see what you get. So remember, what you're calculating here is the velocity of the electrons in an electron gun with an accelerating voltage of 5,000 volts. Now, please remember that your answer should be sensible. And if it's not a sensible answer, like 12 times 10 to the 19, or something like that, just made up that number, do it again, because it clearly can't be faster than the speed of light. Okay guys, ready for the big reveal. Now, if you haven't done the maths yet on your calculator, pause the video now and do the maths. Okay, and then play it again when you're ready. So, there it is. Okay, so I've put numbers into this equation. You'll notice I've done 2VE, so 2 times the accelerating voltage multiplied by the charge on the electron that was accelerating, and I've divided by the mass of an electron. Yes, it's the rest mass, I know, but we're not in the business here of doing relativistic calculations, so it will do as an estimate. And we get 4.2 times 10 to the 7 meters per second. Now, those of you who know me well will say, well, actually, that's unlike you. You're obsessed by engineering notation, that ENG button that I keep going on about on your calculator. 42 times 10 to the 6 meters per second. But I've done it for once in standard form because I'm looking at that. Okay, so it's times 10 to the 7. So do you remember what I said about it being a sensible number? This is about 1/10 the speed of light. So that's possible. It's possible for the velocity to be about 1/10 the speed of light. So I'm sort of feeling that this number is okay. Obviously, I haven't been thinking about significant figures and things like that here. It's just a quick back of the envelope calculation. So we've got the velocity of our electrons. We know their rest mass. Okay. So if we multiply their velocity by the rest mass, we'll have their momentum. And let's stick that into de Broglie's equation. So we're almost there. You remember that lambda of the electron, the de Broglie wavelength, is h upon rho, where rho is the momentum, so mv. So what I'd like you to do now is to get your calculator out and put some numbers into this equation. So we know Planck's constant, we know the rest mass of the electron that I'll have to do in this case, and we know the velocity that the electron was moving at, having gone through the electron gun in the tube. And if you remember, it showed diffraction properties, so the electron was behaving like a wave. And I'd like you now to calculate the de Broglie wavelength. So pause the video, okay, do the calculation, and then press play again. So I hope you're back now. I'm going to reveal what I did. Okay, so I put the numbers into the equation, into the de Broglie equation. So there's our h, there's our mass of the electron, and there's the velocity that we calculated it being at. Okay, and there is the de Broglie wavelength of our equation. So we've calculated the wavelength of the electron moving down through the electron gun and hitting the graphite, which are the little atoms that behave like a grill. Now, that could just be pure maths, but it has a real meaning, of course, because look, it's about 2 times 10 to the minus 11. Figures in the order of 10 to the minus 11, 10 to the minus 10, these are the gaps between atoms. So it's unsurprising, I suppose, if we know about de Broglie's work, that the electron did diffract going through graphite, because the spacing between atoms will be somewhere near this figure. So if you think about it, we can never produce a grating that is small enough for humans to diffract through, but we can produce a grating that electrons will diffract through. So that's a little bit of an introduction to the de Broglie equation. And just remember what it does. It's really, really clever. It brings together the particle-wave duality ideas, that a particle can behave like a wave, and a wave, the de Broglie wave function, can be calculated for a particle moving with a certain momentum. Good. Anyway, I hope you found that really useful. Play with the videos a few times so you really get your head around this. And in fact, for you guys, that would have been my last lesson of the lower sixth course, because that's where the lower sixth ends, and we would begin the second year A level. So we might get started on that soon. Anyway, I'll see you next time.